Gravity is the force that governs the cosmos, yet we still do not understand how it truly works. Einstein's theory of general relativity was a monumental leap, but it left behind profound mysteries. This is the gravity illusion, the unsettling idea that our most basic experience of this force could be a cosmic mirage. By the end of this journey, you will see the universe through a completely new lens, discovering why the most brilliant minds in physics are still stumped. We will uncover why galaxies spin too fast for the visible matter holding them, and what strange energy is ripping the cosmos apart at the seams. What do you believe is the most fundamental truth about our reality? A wild-haired patent clerk quietly reimagined the cosmos. Albert Einstein did not just refine our understanding of gravity, he completely reinvented it. Before him, we saw gravity as a simple, invisible force pulling objects together, much like Isaac Newton did with his famous apple. But Einstein's genius was to propose something far more radical. He suggested that gravity is not a force at all. Instead, it is a consequence of the very shape of the universe. Think of the fabric of the cosmos as a vast, taut rubber sheet. When you place a heavy object like a bowling ball onto that sheet, it creates a deep dimple. Now, if you roll a marble nearby, it will not travel in a straight line. It will spiral inward, following the curve created by the bowling ball. That marble is not being pulled by a mysterious force. It is simply following the path laid out by the warped surface. This is the essence of general relativity. Space and time are woven together into a single, flexible fabric called space-time, and mass tells this fabric how to curve. That curvature, in turn, tells objects how to move. This idea is rooted in a simple but profound thought experiment known as the Equivalence Principle. If you were in a windowless elevator accelerating upwards through space, you would feel your feet pressed to the floor, indistinguishable from the feeling of gravity on Earth. Einstein realized that gravity and acceleration are, in a fundamental sense, the same experience. From this single insight, an entire new cosmos emerged. His equations predicted bizarre and magnificent phenomena like black holes, regions of space where gravity is so intense that not even light can escape. They also foretold gravitational waves, ripples in spacetime itself, sent across the universe by cataclysmic events like colliding black holes. For decades, these were just mathematical curiosities. Yet, in recent years, we have detected these waves directly, a stunning confirmation of a theory conceived in a single human mind. But here is where the story takes a turn. This magnificent theory, which perfectly describes the dance of planets and the bending of starlight, begins to fray at the edges. When we peer into the heart of a black hole, or try to understand the universe in its first fleeting moments after the Big Bang, the mathematics of general relativity breaks down, clashing violently with the rules of the quantum world. The very theory that gave us our deepest understanding of gravity also built the walls of its own prison. Its greatest successes set the stage for its most profound failures. Einstein's beautiful fabric of spacetime seems to unravel when we enter the bizarre realm of the very small. In the quantum world, the rules are not about smooth curves and predictable paths. Instead, particles pop in and out of existence, governed by chance and probability. An electron does not have a single location. It exists as a cloud of possible positions until the moment we observe it. This is the domain of quantum mechanics, and it describes the fundamental building blocks of our universe with breathtaking accuracy. Yet, it paints a picture that is fundamentally at odds with Einstein's cosmic stage. Here lies the great conundrum of modern physics. We have two theories, each spectacularly successful in its own domain, that cannot be merged into one. General relativity describes the gravity that sculpts galaxies and bends light, a force born from the geometry of spacetime itself. Quantum mechanics describes the other three fundamental forces, the ones that hold atoms together and govern radioactive decay. The problem is that gravity refuses to play by the quantum rules. When physicists try to describe gravity using the mathematics of quantum field theory, the equations spit out nonsensical infinities. Calculations blow up, becoming useless. This is what physicists call non-renormalizability. It means the math cannot be tamed to produce a sensible, finite answer. Gravity in the quantum realm becomes a mathematical monster. Imagine trying to combine the rules of a grand, sweeping symphony with the chaotic, improvisational energy of a jazz solo. Both are music, but their core languages are incompatible. That is the scale of the problem facing physicists. The late Stephen Hawking spent decades wrestling with this very issue, particularly at the edge of a black hole, where the immense gravity of relativity meets the fuzzy uncertainty of quantum particles. He realized that without a unified theory, our comprehension of reality is fundamentally incomplete. This is not just an academic debate. The conflict becomes glaringly apparent in the first moments of the Big Bang, when the entire universe was smaller than a single atom, and in the mysterious heart of black holes. In these extreme environments, the smooth fabric of spacetime must somehow be woven from the frantic jitter of quantum particles. But how can a continuum, a seamless sheet, be built from discrete, probabilistic grains? The gravity illusion deepens, suggesting that our perception of space and time as continuous may be just that, an illusion, a shadow of a much stranger truth. Galaxies should tear themselves to shreds. The outer stars, whipping around a galactic center, move at such tremendous speeds that the gravity from all the visible stars, gas, and dust is not nearly enough to hold them in orbit. According to the straightforward math of gravity, these galaxies should be flinging their stars into the void, yet they remain perfectly intact. Something else must be there, providing an immense, unseen source of gravity. Astronomer Vera Rubin provided the most compelling evidence for this, meticulously mapping the rotation of galaxies and finding their outer regions spinning just as fast as their inner cores. This was a direct violation of expectation. It was as if the entire solar system revolved around the Sun, with Pluto moving at the same speed as Mercury, a scenario that would require a hidden force we cannot see. This invisible glue holding galaxies together is what we now call dark matter. We know it exists not only from galactic spins, but from the way it bends the fabric of spacetime itself. This phenomenon is called gravitational lensing. Just as a curved piece of glass can distort the light from a distant street lamp, the gravity of a massive object, like a galaxy cluster, can warp the light from objects far behind it. Sometimes this creates multiple images of a single quasar, or stretches a galaxy into a faint, luminous arc. When astronomers measure the amount of lensing, they find that the mass required to create such a dramatic bend is far greater than the mass of all the visible matter they can detect. There is a vast, unseen halo of something surrounding galaxies, something that interacts with the universe only through gravity. It does not emit, absorb, or reflect any light, making it completely transparent and utterly mysterious. This presents a direct challenge to Einstein's theory. General relativity is spectacular at describing how mass curves spacetime, but it is silent on what this dark matter actually is. The theory tells us how the stage is bent, but it does not account for the main actor hiding in the shadows. For decades, physicists have searched for the proposed particle that could make up this substance. hunting for faint interactions in deep underground laboratories or watching for telltale signals in particle colliders. So far, every experiment has come up empty. This persistent failure has led some scientists to wonder if the problem lies not with an unseen particle, but with our understanding of gravity itself. Perhaps on the vast scales of galaxies, Einstein's equations need a subtle tweak, and gravity behaves differently than we thought. This idea, known as modified Newtonian dynamics or MUND, suggests that the illusion is not dark matter, but our incomplete grasp of the gravitational force. Whether it is an unknown particle or a modification to relativity, the existence of dark matter is a glaring clue in our cosmic puzzle. It screams that our map of the universe is missing a fundamental ingredient, a hidden architecture that shapes everything we see. Yet, just as we grapple with this invisible scaffold holding the cosmos together, an even more baffling discovery emerged, one that points to a force working in the opposite direction, not pulling the universe inward, but relentlessly pushing it apart. The universe is not just expanding, it is accelerating. In the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter, made a discovery that sent shockwaves through the world of cosmology. They were observing a specific kind of stellar explosion, a Type I, a supernova, which acts as a standard candle, a beacon of known brightness across cosmic distances. By measuring how much dimmer these supernovae appeared, they could calculate precisely how far away they were, and by measuring the redshift of their light, they could determine how much the universe had stretched since the explosion. They expected to find that the expansion of the universe was slowing down, gradually braked by the collective gravity of all matter pulling everything inward. The data revealed the opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone predicted. The expansion of the cosmos was not slowing, it was speeding up. Something was overpowering gravity, acting as a cosmic accelerator. This something was given a name: dark energy. Think of it like this: you throw a ball straight up into the air. You expect it to slow, stop at its peak, and fall back to Earth. Now imagine you throw that ball, and instead of slowing down, it starts flying upwards faster and faster, defying the pull of gravity entirely. That is what dark energy is doing to the entire universe. It is a repulsive force, a kind of anti-gravity woven into the fabric of space itself. This discovery was a monumental surprise because it presented a direct challenge to a very specific prediction of general relativity. Einstein's equations, in their purest form, did not naturally allow for such a phenomenon. In fact, Einstein himself had once inserted a fudge factor into his equations, which he called the cosmological constant, to force the universe to be static and unchanging. He later called this his greatest blunder when the expansion of the universe was discovered. Ironically, that same cosmological constant is now the leading candidate to explain dark energy. It represents a constant energy density, an inherent pressure intrinsic to empty space that drives the expansion faster and faster. But is it really that simple? Is dark energy just this static constant, or is it something more dynamic and strange, a field that changes over time? The truth is, we do not know. The nature of dark energy remains one of the most profound mysteries in physics. It deepens the gravity illusion dramatically. We thought we understood how mass and energy shaped the cosmos through gravity, but now we find that the vacuum of space itself seems to possess a repulsive force, a fundamental push that is actively winning the cosmic tug of war against the pull of all matter. This means our grasp of the most basic forces is not just incomplete, it might be fundamentally flawed. The interplay between the attractive force of gravity and the repulsive force of dark energy sets the stage for the entire fate of the cosmos, and it forces us to consider possibilities far stranger than Einstein ever imagined. Deep within the black hole's final embrace, the equations of general relativity lead to a terrifying destination. They predict a point of infinite density, a location where the curvature of spacetime becomes an endless vertical spike. This is the singularity, a place where all the known laws of physics cease to function. It is a mathematical scream, a sign that our most powerful theory of gravity has reached its absolute breaking point. This is not just a feature of black holes. The very same problem appears when we rewind the cosmic clock to the very beginning. The Big Bang itself emerges from a singularity, a point of infinite heat and density from which the entire universe was born. If the theory cannot describe the start of everything or the final state of a collapsed star, then what does it truly explain? Physicist Roger Penrose, working alongside Stephen Hawking, proved that singularities are not mathematical flukes. They are an unavoidable consequence of general relativity under extreme conditions. They are the places where the smooth fabric of spacetime is punctured, revealing a profound ignorance at the core of our knowledge. The existence of these points screams that gravity, as Einstein described it, is an incomplete picture. It works perfectly everywhere except for the most important places of all, the origins and the ultimate endings. This is the heart of the singularity problem, a direct confrontation with the gravity illusion. Our perception of a well-behaved cosmic stage shatters, forcing us to ask what truly happens when space and time are crushed out of existence. To resolve these infinities, we need a theory that can operate where relativity fails, a theory that can handle the frantic quantum jitter that must dominate at such scales. This quest leads us to a place where even time, the most reliable constant in our lives, begins to warp and lose all meaning. The same theory that predicts these terrifying singularities also gave us one of the most beautiful confirmations in all of science, the detection of gravitational waves. These are the ripples in the fabric of spacetime itself, first observed directly in 2015 by the LIGO Observatory. When two black holes spiral into each other in a final, violent dance, they do not send out a flash of light. Instead, they shake the universe, sending tremors through spacetime that travel at the speed of light. By the time these waves reach us, over 1 billion light-years later, the disturbance they cause is almost impossibly small, smaller than the width of a single proton. That we can detect such a minuscule wobble is a triumph of human ingenuity and a stunning validation of Einstein's vision of a dynamic, flexible cosmos. This discovery also confirms another strange prediction, time dilation. According to general relativity, time itself is not a universal constant. It flows at different rates depending on the strength of the gravitational field. A clock placed closer to a massive object like Earth will tick ever so slightly slower than a clock farther away. We experience this every day without realizing it. The GPS satellites that guide your car have atomic clocks on board, and because they are in a weaker gravitational field high above the planet, their clocks run faster than identical clocks on the ground. If engineers did not constantly correct for this relativistic time warp, your GPS would be off by several miles within a single day. The system only works because we trust Einstein's equations to be precisely right. Yet, even as we celebrate these confirmations, the data holds subtle clues that might lead us beyond Einstein's theory. The gravitational wave signals from some collisions appear to have features, slight ringing and echoes, that some physicists argue could hint at exotic possibilities, like the fuzzy, quantum gravitational structure of a black hole's event horizon. Could these ripples carry imprints of physics that general relativity cannot explain? Experts working with LIGO and other observatories are actively looking for any deviation, any tiny anomaly in the wave patterns that does not fit the pristine predictions. Finding one would be like discovering a single wrong note in a symphony we thought was perfect, a small crack in the foundation that reveals a deeper layer of reality. The very waves that so powerfully prove Einstein right are now our most sensitive tools for probing the places where his theory might be wrong. This search takes us from the colossal scale of colliding black holes down to the most fundamental level of existence, a realm where the smooth fabric of spacetime must somehow be woven from the frantic, probabilistic dance of the quantum world. A tiny magnet can lift a paperclip, effortlessly defeating the gravitational pull of our entire planet. This simple fact reveals a staggering cosmic imbalance. Gravity is not just slightly weaker than the other fundamental forces, it is unimaginably feeble. The electromagnetic force that holds atoms together is about 1,000 trillion times stronger than gravity. This is the hierarchy problem, one of the most baffling puzzles in all of physics. If the forces are the fundamental ingredients of our universe, why is the recipe so lopsided? Why is gravity, the force that sculpts galaxies and holds planets in orbit, almost a ghost in the machine when compared to the forces governing the atomic world? This weakness is not a minor detail, it is a deafening clue that our perception of gravity is deeply flawed. Some of the brightest minds in theoretical physics, like Nima Arkani-Hamed, have proposed a radical solution. What if gravity only seems weak because it is not entirely confined to our reality? Imagine our three-dimensional universe as a vast membrane, a cosmic sheet floating within a higher dimensional space. In this picture, the other forces, like electromagnetism, are stuck on our membrane, but gravity, born from the geometry of spacetime itself, can leak out. It can spread its influence into these extra, unseen dimensions. From our perspective, this leakage would make gravity appear diluted. Its true strength spread so thin across the bulk of higher dimensional space that we only feel a faint echo of its power. This is not science fiction, it is a core idea in string theory, which attempts to unite gravity with quantum mechanics by proposing that the fundamental constituents of reality are tiny, vibrating strings. To make the math work, these strings require extra spatial dimensions, curled up into sizes so infinitesimally small that we could never perceive them directly. The multiverse hypothesis offers another, equally mind-bending possibility. Perhaps the strength of the fundamental forces is not a law, but a random accident. In an infinite multiverse of bubbling universes, each with different physical constants, we simply happen to live in one where gravity is exceptionally weak, a cosmic lottery ticket that allowed stars and planets, and eventually life, to form. If gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. This profound weakness, therefore, might not be a problem to be solved, but a prerequisite for our own existence. The hierarchy problem forces us to confront the gravity illusion head-on. It suggests that the force we experience every day is not fundamental, but a mere shadow, a faint projection of a deeper, more potent reality playing out in a realm with more dimensions than we can comprehend. The search for answers does not end with speculative theories, however. It pushes us to look for experimental proof, to find cracks in Einstein's framework that might reveal the true, hidden nature of the force that binds the cosmos. What if the invisible dark matter scaffolding is an elaborate fiction? A rival idea known as modified Newtonian dynamics, or MUND, proposes exactly that. It dares to suggest that we do not need to invent a mysterious, unseen substance to hold galaxies together. Instead, the problem lies with our most basic understanding of gravity itself. The theory, championed by physicist Mordechai Milgrom, posits that Newton's law of gravity, the very one Einstein refined, begins to break down under certain conditions. Specifically, when the gravitational pull becomes incredibly weak, such as in the sparse outer reaches of a galaxy, the force stops fading with the square of the distance. It transitions to a different, persistent strength. This single tweak to the equations can perfectly explain why the outer stars of a galaxy orbit so quickly, all without a single particle of dark matter. The math is startlingly simple and elegantly reproduces the flat rotation curves that Vera Rubin observed. For its advocates, MUND is not just a patch, it is a more natural explanation. It resolves galactic anomalies that dark matter models struggle with, suggesting that the gravity we think we know is merely an approximation of a deeper truth. Yet, MUND faces its own profound challenges. It struggles to explain the gravitational lensing we see from massive galaxy clusters, which seems to require far more mass than MUND alone can provide. It also has difficulty fitting neatly into the broader picture of the universe's evolution as described by cosmology. The cosmic microwave background, the faint afterglow of the Big Bang, has a pattern that strongly supports the existence of dark matter. So, we are left with a fascinating standoff. Does the universe contain a hidden, invisible form of matter that dominates its structure, or are the laws of gravity we have relied on for centuries subtly wrong on the largest scales? This is not a minor academic dispute, it is a battle over the fundamental rules of the cosmos. One side searches for a hidden actor in the shadows, while the other insists the stage itself is behaving in a way we never anticipated. The very existence of this debate proves that the gravity illusion is real, forcing us to question whether our most trusted equations are complete. To settle this, we must descend from the scale of galaxies down to the most fundamental level of reality, where the fabric of spacetime itself must be born from the chaotic quantum realm. What if space and time are not smooth and continuous, but made of tiny, indivisible pieces? This is the startling proposal of loop quantum gravity, a theory that attempts to stitch the quantum world directly into the fabric of the cosmos. Imagine the universe not as a seamless sheet, but as a woven tapestry. Each thread in this tapestry is a tiny, one-dimensional loop, a fundamental stitch in the fabric of reality. These loops, woven together in a vast dynamic network, create the very structure of space itself. According to theorists like Carlo Rovelli, space is not a background stage where events unfold. It is this evolving web of relationships. It is granular or pixelated, but on a scale so incredibly small that it appears perfectly smooth to us, just as a digital photograph looks continuous from a distance. This granularity has a profound consequence. It prevents the formation of singularities. There is no point of infinite density inside a black hole because you cannot pack matter into a volume smaller than the smallest possible stitch in the quantum fabric. Instead of a terrifying infinity, the theory predicts a bounce, a point where collapse reverses into an explosive new beginning. This could mean that our Big Bang was not the absolute beginning, but merely one turn in an endless cosmic cycle. Loop quantum gravity is also background independent, a technical term with a simple, beautiful meaning. It says that space and time do not exist as a pre-existing container. The loops themselves define what space is and how time flows. They are the actors that build the stage as they perform, creating the geometry of the universe from the bottom up. This stands in stark contrast to its main competitor, string theory. While string theory proposes extra, curled-up dimensions to unify the forces, loop quantum gravity works with the three dimensions of space and one of time we already experience. It does not seek to add new layers to reality, but to redefine the very nature of the space we know. In this view, gravity is not a fundamental force in its own right. It emerges as a consequence of this tangled quantum geometry, a cosmic illusion born from the collective behavior of countless tiny loops. The force that holds planets in orbit is simply the shape of this quantum tapestry. Yet, for all its elegant promise, this theory is not the final answer. It struggles to describe how the smooth spacetime of general relativity reliably emerges from its quantum building blocks, and it has yet to successfully incorporate the other fundamental forces. The quest to complete the picture of quantum gravity leads us down a different and even more ambitious path, one that replaces the solid particles of matter with unimaginably small, vibrating strings. String theory replaces the solid dots of matter with shimmering loops of pure energy. The fundamental building blocks of the universe, according to this radical idea, are not point-like particles but unimaginably small, vibrating strings. What makes an electron and a quark is not a difference in substance but a difference in vibration. Each tiny string, trillions of times smaller than an atom, hums with a specific resonant frequency, and that frequency determines everything it is and does. One note might be an electron, another a photon of light. In this symphony of the very small, gravity finally finds its place. A particular vibration of a closed string loop would manifest as the graviton, the hypothetical particle that carries the gravitational force. This is the profound promise of string theory. It does not just add gravity to quantum mechanics. It naturally produces gravity from the same basic ingredients. The force that bends the cosmos emerges from the same vibrational dance as the forces that bind atoms. This elegant unity, championed by thinkers like Brian Greene, suggests that the gravity we experience is not an illusion of geometry, but a melody played on the cosmic strings. Yet, this beautiful harmony comes with a staggering price. For the mathematics of string theory to work, the universe cannot have only the three spatial dimensions we know. The equations require extra dimensions, perhaps 6 or 7 more, all curled up into shapes so tiny and complex that they are completely hidden from our view. Imagine a garden hose seen from a great distance. It looks like a simple one-dimensional line. Only when you get very close do you see its circular, two-dimensional surface. The extra dimensions of string theory are theorized to be curled up with a similar but far more intricate compactness. The theory's incredible ambition is also its greatest weakness. These extra dimensions and the vibrating strings themselves exist at energy scales far beyond the reach of any particle collider we can build. After decades of intense work, string theory has yet to make a single testable prediction that can be verified in a laboratory. For its critics, it remains a magnificent piece of abstract mathematics, a theory of everything that risks becoming a theory of nothing we can prove. It stands as a monument to human imagination, a potential map to a deeper reality where all forces are one. But without a path to experimental confirmation, the map remains beautifully drawn, yet frustratingly untested, leaving us to wonder if the ultimate unity of the cosmos will forever lie just beyond our grasp. Gravity may not be a fundamental force at all, but a cosmic mirage born from chaos. This radical idea, known as emergent gravity, suggests that what we perceive as gravity is merely a side effect, an illusion that emerges from the relentless drive of the universe toward disorder, a concept we call entropy. Think of a glass of ice water left on a counter. The ice cubes do not melt because some special force is pulling them apart. They melt because the universe statistically favors a state where molecules are more jumbled and disordered. The transition from orderly ice to chaotic water is driven by an increase in entropy. Now, apply this principle to the fabric of spacetime itself. theorists like Eric Verlin propose that space is not a smooth, pre-existing stage, but is built from microscopic, information-rich components, a kind of fundamental code. When a massive object like a star is placed within this structure, it disturbs the arrangement of this information. The system's natural tendency is to move toward maximum disorder, and this statistical push to reorganize and maximize entropy manifests as what we feel as the gravitational force. An object falling toward Earth is not being pulled, it is being guided along a path of increasing entropy, following the statistical tendency of the underlying information to become more jumbled. This view completely reframes our search for understanding. It suggests gravity is not a fundamental interaction to be quantized, but a collective thermodynamic effect, much like how the pressure of a gas emerges from the chaotic motion of countless molecules, not from any fundamental pressure force. This startling perspective offers a potential solution to the dark matter puzzle. Rather than invoking an invisible substance, emergent gravity naturally produces extra gravitational effects in the low-density regions of galaxies, precisely where we observe stars orbiting too fast. The apparent pull of dark matter could simply be the entropy of the underlying spacetime structure responding to the presence of visible matter. While this idea is profoundly elegant, it remains highly theoretical and fiercely debated, a beautiful map that has yet to be fully tested. But how do we move from these breathtaking theories to hard, experimental proof? The search for answers is pushing our instruments to their absolute limits, hunting for the faintest whispers of new physics in the cosmos. A tiny, unexpected drift can unravel our most trusted maps of reality. For decades, our most precise spacecraft have been charting the solar system, and in their flawless trajectories, scientists have occasionally spotted a faint, persistent whisper of something wrong. The Pioneer 10 and 11 probes, after swinging past Jupiter and Saturn, began to slow down just a little more than expected. This minuscule deceleration, less than a billionth of the gravity we feel on Earth, became known as the Pioneer Anomaly. For years, it haunted orbital mechanics, a ghost in the machine that Einstein's equations could not explain. Was it a subtle thrust from heat radiating off the spacecraft's own electronics, or was it the first hint of a modification to gravity at the largest scales? While most now attribute it to thermal effects, the mystery itself was a powerful reminder. Our theories are only as strong as the data that tests them. Similar, even fainter glitches appear in the orbits of planets themselves. Precise laser ranging to the Moon reveals that its orbit is widening at a rate that differs from predictions by a hair's breadth. Mercury's long-observed perihelion precession was the first great validation of general relativity. But what if other, smaller orbital quirks are still hiding in the data, waiting for instruments sensitive enough to find them? These are not failures of science, they are its lifeblood. Every unexplained decimal point, every tiny deviation in a spacecraft's path, is a potential crack in the foundation. Why would a force as fundamental as gravity show these slight variations? Could there be undiscovered particles interacting with matter, or perhaps unseen dimensions subtly altering the gravitational field over vast distances? To find out, physicists are designing experiments of breathtaking precision. Space-based observatories like LISA will use lasers to measure the distance between free-floating cubes millions of miles apart, hunting for the ripples from merging supermassive black holes. Any anomaly in those waves could be a direct signal from the quantum gravity realm. Atomic interferometers here on Earth are now so sensitive they can detect the difference in gravity's pull between the top and bottom of a single centimeter. These are not just incremental improvements, they are leaps into a new domain of measurement, where the fabric of spacetime itself is placed under a microscope. The quest to explain these outliers is what pushes our understanding forward. It forces us to build better tools and ask deeper questions, transforming minor discrepancies into the very clues that could shatter the gravity illusion for good. And there is no more extreme environment to test these ideas than the ultimate gravitational forge, the edge of a black hole. A black hole's event horizon is the ultimate point of no return, a boundary beyond which not even light can escape. According to Einstein's general relativity, anything that crosses this threshold is lost forever, crushed into the singularity and removed from our universe. But the quantum world has a fundamental rule: information cannot be destroyed. Every particle carries information about its properties, and quantum mechanics insists this information is never truly erased, only scrambled and rearranged. This creates a devastating conflict known as the black hole information paradox. If a book falls into a black hole, does the information printed on its pages simply vanish when the black hole eventually dies? Stephen Hawking discovered that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation, however, appears to be completely random, carrying no information about what fell in. If the black hole evaporates entirely, leaving behind only this featureless radiation, then the information is irretrievably lost, violating a cornerstone of quantum physics. The paradox suggests a terrifying choice. Either general relativity is wrong and information can escape a black hole, or quantum mechanics is wrong and information can be destroyed. Both options undermine the foundations of modern physics. To resolve this, physicists like Leonard Susskind proposed a truly mind-bending idea: holography. Imagine the information contained within a three-dimensional space, like the interior of a black hole, being perfectly encoded on its two-dimensional surface, the event horizon. It is like taking every detail of a sculpture and faithfully storing it as a complex painting on the surface of that sculpture. The information about the book that fell in is not lost inside. It is smeared across the black hole's surface, preserved in the intricate structure of the horizon itself. When Hawking radiation is emitted, it slowly and subtly carries this encoded information back out into the universe. The information was never truly gone. It was just translated into a form we could not initially recognize. This holographic principle radically redefines the nature of reality. It suggests that our perception of a three-dimensional world may be a projection from a two-dimensional surface at the universe's boundary, a cosmic illusion of depth. The information paradox is a direct assault on the gravity illusion, proving that our classical picture of space-time as a smooth, continuous fabric is fundamentally incompatible with the quantum nature of information. Solving this puzzle would require a theory where space-time and information are two sides of the same coin, forcing a revolution in our understanding of reality itself. This struggle to preserve information does not end at the edge of a black hole. It extends to the very horizon of our entire observable universe. The energy contained within empty space should be immense. According to our best theories of the quantum world, the vacuum is not a silent void but a seething, bubbling foam. Virtual particles flicker in and out of existence in a frantic, relentless dance, and all this activity imbues every cubic centimeter of nothingness with a staggering amount of energy. This is the energy that theorists believe drives the accelerating expansion of the cosmos, the dark energy we represent with Einstein's cosmological constant. Yet when we calculate how powerful this vacuum energy should be, the result is catastrophically wrong. The prediction from quantum field theory is larger than the value we observe by a factor of 1 followed by 120 zeros. This is not just a small error, it is the most colossal failure of prediction in the entire history of science. To grasp this number, imagine the difference in scale between a single proton and the entire observable universe. The discrepancy for the cosmological constant is a trillion times larger than that. How can the theoretical expectation and the real-world measurement be so impossibly out of sync? This is the cosmological constant problem, and it screams that something fundamental in our understanding is broken. Either our math for the quantum vacuum is deeply flawed, or our interpretation of what the cosmological constant actually represents is completely misguided. The universe appears to be finely tuned to an almost impossible degree. If the vacuum energy were just slightly stronger, the repulsive force would have ripped galaxies, stars, and even atoms apart before they could ever form. If it were slightly weaker and negative, the cosmos would have collapsed back on itself in a swift, violent crunch. Our very existence seems to hinge on this cosmological constant being almost exactly zero, a breathtakingly precise cancellation of unimaginably large opposing numbers. This fine-tuning is so extreme that some physicists, like the Nobel laureate Steven Weinberg, have considered a startling possibility. Perhaps there is no deeper reason for the value we observe. In a vast multiverse where countless universes bubble into existence with different physical constants, we naturally find ourselves in one of the rare habitable pockets where the numbers allow for life. This anthropic reasoning is deeply controversial, as it suggests some questions may not have a fundamental physical answer. For others, the problem is a direct clue, a glaring signpost pointing toward a new law of physics. The solution might require us to understand that the vacuum energy calculated by particle physics and the cosmological constant of general relativity are not the same thing, that some unknown symmetry or mechanism forces them to cancel out. This immense gap between prediction and reality is the ultimate reinforcement of the gravity illusion. It reveals a profound disconnect between our understanding of the large and the small, between the quantum world and the cosmic stage. The force that shapes the entire universe on the grandest scale is dictated by a number we cannot begin to explain, a haunting reminder that our most brilliant theories are still just a shadow of a deeper, hidden truth. This mystery only deepens when we rewind the cosmic clock to the very beginning. The initial moments of the cosmos were a period of unimaginable violence. In a fleeting fraction of a second, the universe underwent a growth spurt of epic proportions, expanding by a factor of at least 10 to the 26th power. This was cosmic inflation, a concept pioneered by Alan Guth, who described it as the universe's ultimate free lunch. A hypothetical energy field known as the inflaton is thought to have powered this exponential burst, stretching a subatomic speck of space into a macroscopic domain faster than the speed of light. This idea elegantly solves profound puzzles about our universe. It explains why the cosmos appears so uniform in all directions, a mystery called the horizon problem. Without inflation, distant regions of the sky would never have been in contact to equalize their temperature, yet we see the same cosmic microwave background everywhere we look. Inflation solves this by suggesting the entire observable universe was once a tiny, connected patch stretched to astronomical size. It also accounts for the origin of all structure, as microscopic quantum fluctuations in the inflaton field were magnified to cosmic proportions, becoming the seeds for every galaxy, star, and planet we see today. But here is the catch: the mechanism of inflation remains deeply speculative. The inflaton field is a theoretical placeholder, its true nature completely unknown. Its connection to gravity is even more tenuous. While the field's repulsive gravity would have driven the rapid expansion, this is a classic application of general relativity, treating the inflaton as just another form of energy that warps spacetime. The theory does not fundamentally explain why such a field should exist or how it emerges from a more complete theory of quantum gravity. As Guth himself has noted, inflation is a spectacularly successful paradigm, but it is a framework in search of deeper roots. The inflationary epoch represents the highest energy regime we can meaningfully discuss, a realm where gravity and quantum effects were inextricably linked. How did the inflaton field interact with the frantic jitter of the quantum vacuum? Did the fabric of spacetime itself behave differently during this violent stretch? The answers are locked within that first instant, and they likely hold the key to understanding gravity's true nature. This primordial event might be the ultimate expression of the gravity illusion, a period where the force we think we know was acting under a completely different set of rules, its behavior a direct window into a unified reality we have yet to grasp. The smooth stage of Einstein's cosmos dissolves into a frantic, bubbling sea at the smallest imaginable distances. This is the realm of spacetime foam, a concept born from the strange marriage of general relativity and quantum mechanics. At scales a trillion times smaller than an atom, the vacuum of space is not empty or serene. It is a turbulent ocean of probability, where virtual particles and antiparticles constantly flicker into existence, borrowing energy from the void for an impossibly brief moment before annihilating each other. This ceaseless activity is not just a curious side effect, it is the fundamental texture of reality. The physicist John Wheeler envisioned that at this ultimate level, the very concepts of here and now lose their meaning. Spacetime itself becomes a probabilistic, foamy mess, with tiny wormholes and tunnels constantly forming and dissolving. In this foam, the smooth, continuous geometry that Einstein described is merely a large-scale average, a calming of the quantum storm that occurs when we zoom out. The solid ground beneath our feet, the predictable orbit of a planet, all of it is an illusion built upon a foundation of chaotic, random fluctuations. This quantum jitter has a direct and profound consequence for gravity. Every flickering particle pair carries a tiny bit of energy, and according to Einstein's own equations, energy curves spacetime. So this seething vacuum is constantly warping the geometry of the universe on the tiniest scales. The collective gravitational effect of this infinite sea of virtual particles should, in theory, contribute to the cosmological constant, adding to the dark energy that pushes the cosmos apart. Yet, as we've seen, the calculated value is catastrophically large compared to what we observe. This glaring mismatch is a direct signal that our understanding of this quantum foam is incomplete. Perhaps the foam's structure naturally cancels out most of this energy, or maybe gravity itself behaves differently in this frenzied domain. The foam suggests that gravity's apparent continuity is not fundamental. It emerges much like the smooth surface of a lake emerges from the chaotic motion of countless water molecules. We do not perceive the individual molecules, only the collective behavior. In the same way, we do not perceive the spacetime foam, only the smooth, classical force of gravity that arises from it. Detecting this foam directly remains a monumental challenge, as it operates at scales far beyond our current technology. But the idea itself is a powerful guide, forcing us to rewrite our equations for a universe where space and time are not a passive backdrop, but an active, dynamic, and deeply strange participant in the cosmic drama. This vision of a frothing vacuum pushes us to the very limits of reality, where the distinction between something and nothing blurs into a single, unified, and vibrating whole. Our most reliable constant might be the greatest illusion of all. Time flows for us in one direction, from a fixed past to an uncertain future, yet this experience shatters completely at the frontiers of physics. In Einstein's general relativity, time is dynamic and malleable, a flexible dimension woven into the fabric of spacetime that can stretch and slow down. But in the quantum world, time is rigid and absolute, a fixed background against which the probabilistic dance of particles unfolds. These two visions are irreconcilable. When we try to build a theory of quantum gravity, this clash becomes a profound crisis known simply as the problem of time. The equations of general relativity are timeless, describing a static, four-dimensional block universe where the past, present, and future all exist simultaneously. In this view, the flow of time is a human psychological artifact, not a feature of the fundamental world. But how can this be reconciled with our direct experience of change and causality? How can a theory that has no time account for the obvious fact that the universe evolves? This is the central struggle for theories like loop quantum gravity. Their core equations are timeless, describing the relationships between the quantum loops of space without any reference to a clock. To recover the time we know, physicists must find a way for time to emerge from the changing relationships between events. Think of a movie. The film itself exists all at once, every frame present on the reel. But the experience of the story, the flow of time, only happens when the projector runs, creating a sequence from one frame to the next. In this analogy, the universe is the complete film reel, and our consciousness is the projector, creating the illusion of a moving present. Philosopher of physics Carlo Rovelli takes this idea further, proposing that time is not a fundamental dimension but a consequence of our limited macroscopic perspective. At the most basic level, the universe might be a network of events, and what we perceive as time is merely the result of the quantum interactions between them. There is no universal clock ticking in the background, only countless localized processes that give rise to the appearance of sequence and duration. This temporal ambiguity is a core part of the gravity illusion. Our perception of time's smooth passage is deeply entangled with gravity itself. A clock ticks slower in a stronger gravitational field, a confirmed fact of general relativity. If gravity is not fundamental but emerges from a deeper, timeless quantum structure, then time itself must emerge alongside it. We are left with a staggering possibility that the relentless march of time, the very foundation of our reality, is a cosmic side effect. Resolving this problem would not just complete physics, it would fundamentally reshape our understanding of causality, memory, and our own place in a universe that may not, at its heart, know the meaning of now. This forces us to ask if the solution requires not just a new theory of gravity, but a complete overthrow of our most cherished concepts. Our universe could be a solitary island, a vast membrane adrift in a higher dimensional sea. This is the core of Brainworld scenarios, a radical reimagining of reality where the three dimensions we know are not the whole story. In this picture, our entire cosmos is a three-dimensional brain, short for membrane, existing within a larger, higher-dimensional space called the bulk. The matter we are made of, the light we see, all the particles of the standard model are trapped on our brain like ink stains on a sheet of paper. They cannot leave the surface. But gravity, born from the geometry of spacetime itself, is different. It is not confined. It can leak off our brain and spread out into the extra dimensions of the bulk. From our perspective, stuck on the membrane, this leakage makes gravity appear incredibly weak. Its true strength is diluted, spread thin across realms we cannot perceive. Think of a powerful sound made in an enormous, open field. By the time the sound waves reach you, they are just a faint whisper. In the brain world, gravity is that whisper, its full voice lost to the vastness of the bulk. This elegantly solves the hierarchy problem, explaining why gravity is so feebly weak compared to the other forces. specific models, like the one proposed by physicists Lisa Randall and Raman Sundaram, calculate this effect with precise mathematics. In their model, the warped geometry of the extra dimension can naturally produce this severe dilution, meaning the fundamental scale of gravity could be much closer to the other forces, resolving the immense cosmic imbalance. The implications ripple outward, challenging our need for dark matter. Perhaps the extra gravitational effects we attribute to an invisible halo are actually the influence of gravity leaking away, or even the gravitational pull from distant matter on a parallel brane in the bulk. Furthermore, the way gravity propagates in these extra dimensions could subtly modify its behavior on cosmic scales, offering an alternative to Einstein's relativity without inventing new particles. These are not untestable fantasies. If extra dimensions exist, they could reveal themselves in powerful particle colliders like the Large Hadron Collider. One predicted signature is the production of microscopic black holes, which would instantly evaporate in a shower of particles. Another is the appearance of gravitons, the carriers of gravity, that effectively disappear into the bulk. While such discoveries remain elusive, the search continues, pushing our machines to their limits. Brainworlds present a profound challenge to the gravity illusion. They suggest that the force we feel, the curvature that guides planets, is not fundamental. It is a shadow, a limited projection of a richer, higher-dimensional reality playing out just beyond the veil of our perception. This forces us to ask if the deepest truths of the cosmos are not in the laws we write, but in the hidden dimensions we have yet to see. Sometimes the universe winks at us through a cosmic mirage. A massive galaxy cluster can act like a flawed lens, warping the light from galaxies far behind it into multiple, distorted images. This phenomenon, gravitational lensing, is one of general relativity's most spectacular predictions, a direct confirmation that mass bends the path of light. Yet in some clusters, the lensing is too strong. The arcs of light are too bright, the multiple images are too widely separated. The visible matter in the cluster simply cannot account for the profound bending we observe. To make the math work, we must invoke a colossal halo of dark matter, an unseen scaffold that provides the extra gravitational pull. But what if the lens itself is not the problem? What if it is the law of gravity that is subtly miscalibrated? When astronomers meticulously map these anomalies, they find that the distribution of dark matter required to explain the lensing often seems strangely disconnected from the visible galaxies, a ghostly presence that does not quite align with the luminous matter it is supposed to accompany. This is not just a problem with clusters. Even the oldest light in the universe, the cosmic microwave background, carries the imprint of gravity's handiwork. The subtle patterns in this afterglow, the cold spots and hot spots, were shaped by the gravitational pull of all matter, both seen and unseen. The patterns we measure fit beautifully with the dark matter model, but they also leave a door open. Could the same patterns be produced by a modified law of gravity, one that strengthens where the pull grows weak? Each unexplained lensing arc, every mismatch between the predicted and observed bend of light, is a tiny crack in the foundation of our understanding. These are not failures of observation, they are whispers from the edge of physics. They tell us that on the grandest scales, the force that sculpts the path of light itself may be playing by a set of rules we have not yet fully deciphered. The quest to understand these cosmic mirages is driving the next generation of telescopes, instruments designed to measure the bend of starlight with unprecedented precision, hunting for the definitive signature that will either lock dark matter into place or finally force us to rewrite Einstein's equations for the cosmos. This foundational idea that gravity and acceleration are indistinguishable now faces its toughest trials. the Equivalence Principle, a core pillar of Einstein's theory, declares that an object's inertial mass, its resistance to being pushed, is exactly equal to its gravitational mass, its response to a gravitational field. Because of this perfect balance, everything falls at the same rate, a feather and a hammer in a vacuum hitting the ground simultaneously. But is this symmetry truly perfect, or does it begin to crack under the most sensitive scrutiny? Physicists are testing this principle with instruments of breathtaking precision. On Earth, delicate torsion balances measure the gravitational attraction between different materials, watching for any minuscule difference in how they respond. The most stringent tests, however, happen in the pristine quiet of space. The French Space Agency's MICROSCOPE Mission placed concentric cylinders made of platinum and titanium in a near-perfect free fall around Earth. The goal was to observe these test masses for months, monitoring whether one ever began to drift relative to the other. If the platinum cylinder experienced even a trillionth of a % more acceleration than the titanium, it would shatter the equivalence principle. The results were both a triumph and a challenge. After painstaking analysis, the microscope team announced they had found no violation, confirming the principle's validity with unprecedented accuracy. Yet the search continues because the implications of finding a crack are monumental. A violation, no matter how tiny, would be a direct signal of new physics. It could be the fingerprint of a fifth fundamental force, an interaction beyond gravity, electromagnetism, and the nuclear forces. It might reveal the subtle influence of extra dimensions, or offer the first experimental glimpse of how quantum gravity affects tamper with spacetime. For experts in the field, any deviation would mean that Einstein's elegant geometric picture is an approximation, a smooth surface hiding a grainy quantum truth. These experiments are not just technical marvels, they are probes into the heart of the gravity illusion, asking whether the force we experience is truly fundamental or a seamless veil over a far more complex machinery. The relentless drive to test this principle underscores a profound quest to discover if gravity is the same for every piece of matter, in every corner of the cosmos, or if its uniformity is itself part of the grand illusion. Einstein spent the last 30 years of his life chasing a ghost. After his triumphant theory of general relativity, he turned his genius to a single, all-consuming goal, a unified field theory that would weave gravity and electromagnetism into a single, elegant tapestry. He believed that if gravity was the geometry of spacetime, then surely the other forces must also be manifestations of that same cosmic fabric. He worked in near isolation, filling blackboard after blackboard with complex equations, yet the solution perpetually eluded him. He was searching for a mathematical key to the entire universe, but the door remained firmly locked. This dream did not die with him. It became the holy grail of modern physics, the drive to find one master equation, a compact set of symbols that could describe every fundamental interaction, from the nuclear glue holding an atom together to the gravitational pull of a galaxy. Think of it as a cosmic theory of everything, a single set of rules for every particle and every force. The ultimate aim is to see gravity not as a separate, stubborn illusion, but as a natural and inevitable note in a grand, universal symphony. For decades, this quest has been the pinnacle of theoretical work, pushing the very limits of human thought. Yet the path to unification is littered with immense challenges. The forces of nature speak different mathematical languages. Electromagnetism and the nuclear forces are described by a specific kind of symmetry, a set of rules that physicists call gauge symmetries. Gravity, in Einstein's theory, is described by the symmetry of spacetime itself. Unifying them is like trying to write a single legal code that applies equally to the chaotic energy of a bustling city and the serene geometric laws of a planetary orbit. The two frameworks seem to be fundamentally incompatible. This mathematical dissonance is matched by a profound experimental problem. To see the unified nature of the forces, we would need to probe energies so astronomically high that they existed only in the first moments after the Big Bang. Our most powerful particle colliders are like trying to decipher the blueprint of a cathedral by studying a single grain of sand. Physicist Michio Kaku has expressed both the soaring optimism and deep frustration of this pursuit, often stating that while the ultimate equation might be simple enough to fit on a T-shirt, the journey to find it is the most difficult in all of science. Modern attempts like string theory and loop quantum gravity are the latest chapters in this epic struggle. String theory seeks unity by proposing that everything is made of tiny, vibrating strings, with gravity emerging as just one particular resonant note. Loop quantum gravity takes a different path, aiming to rewrite the fabric of space itself in discrete quantum stitches from which gravity would naturally arise. Both are monumental achievements of human imagination, yet both remain frustratingly distant from experimental proof. The philosophical implications of success would be staggering. A verified theory of everything would not just complete our textbook of physics, it would fundamentally reshape our understanding of reality. It would suggest that the cosmos is not a collection of separate phenomena, but a single, coherent, and breathtakingly elegant entity. The gravity illusion would finally dissolve, revealing that the force which shapes the cosmos and the forces that build atoms are, in the end, one and the same. Gravity's stubborn refusal to fit neatly into our models does more than frustrate physicists. It forces a deep philosophical reckoning. For centuries, we assumed that space and time were the ultimate stage, the fixed and absolute background upon which the drama of the cosmos played out. Forces like gravity were simply actors moving across this pre-existing platform. But if gravity is not a fundamental force but an emergent property, then the stage itself is part of the performance. The platform is built by the actors as they perform. This turns our entire conception of reality inside out. Philosopher of physics Tim Maudlin argues that we must distinguish between the fundamental architecture of the world and the effective, higher-level patterns we observe. Our most successful theories, like general relativity, might be brilliantly accurate maps of the territory, but they do not necessarily describe the territory's most basic substance. The smooth, continuous spacetime of Einstein's equations could be a magnificent approximation, a large-scale average of a reality that is, at its heart, discrete, relational, and perhaps even timeless. What does it mean for something to be real if the force that gives it weight is itself a cosmic side effect? Our entire sense of causation, of one event leading to another, is built upon this gravitational framework. If that framework is illusory, then the chain of cause and effect we rely on to make sense of the world might also be a derived concept, not a fundamental law. This line of thinking humbles the very pursuit of knowledge. It suggests that our models, no matter how powerful, are inherently limited by our perspective as macroscopic beings embedded within the system we are trying to understand. We are like fish trying to develop a fundamental theory of water. We are so immersed in it that its true nature is the hardest thing to see. The mystery of gravity, therefore, is not a gap to be filled, but a permanent reminder that the universe is far stranger and more wonderful than our intuitions allow. This philosophical unease is the engine of scientific progress. It pushes us to build more sensitive experiments and to entertain ideas that once seemed like heresy. The practical goal of future research is not just to find the right equation, but to answer a more profound question. Are we discovering the universe's rules, or are we merely deciphering the shadows they cast? Resolving the true nature of gravity would do more than complete a textbook. It would fundamentally redefine our place within an unfolding cosmic story whose deepest truths we are only beginning to glimpse. Atomic clocks now track the flow of time with such fidelity they can detect the gravitational shift created by a single centimeter of elevation. This is the staggering precision of our new tools, instruments designed not just to confirm Einstein's universe, but to scour it for the faintest cracks. In the quiet of space, the Laser Interferometer Space Antenna, or LISA, is being readied. This ambitious mission will use 3 spacecraft, flying in a perfect triangle millions of miles apart, connected by lasers. Their goal is to catch the gravitational waves from events too colossal for Earth-based detectors, like the mergers of supermassive black holes at the dawn of time. Any subtle anomaly in the shape of those spacetime ripples, any echo or harmonic that does not fit the pristine prediction of general relativity, could be the first direct signal from the quantum realm of gravity. It would be a whisper from the other side of the illusion. Back on Earth, another revolution is underway with atom interferometers. These devices exploit the quantum wave nature of atoms, using lasers to split an atom's probability cloud and then recombine it. The resulting interference pattern is exquisitely sensitive to tiny changes in acceleration and gravity. Researchers are using them to measure the gravitational constant with unprecedented accuracy and to search for hypothetical fifth forces that could indicate new particles or extra dimensions. The data from these machines is so clean, so precise, that it transforms gravity from a philosophical abstraction into a quantity you can measure, manipulate, and challenge. Alongside these physical instruments, advances in computing are creating virtual laboratories in silicon. Scientists can now simulate entire universes governed by modified laws of gravity, watching as virtual galaxies form and evolve. They can run the cosmic tape forward under the rules of MUND or emergent gravity, comparing the resulting digital cosmos to our actual astronomical surveys. These simulations do not prove a theory, but they tell us what to look for, guiding our telescopes toward the most telling celestial patterns. The collective power of these technologies is turning the gravity illusion from a theoretical puzzle into a series of empirical questions we are finally equipped to answer. Each precise measurement, each simulated galaxy, and each captured gravitational wave is a potential key, and the next great discovery might not come from a lone genius in a study, but from the collective effort of a global community, including thousands of everyday observers. The deepest mysteries of the cosmos are not reserved for those with advanced degrees. They belong to anyone who has ever looked up at the night sky and wondered. Our collective struggle to understand gravity, this fundamental illusion, sparks a fire of curiosity that powers innovation far beyond the walls of academia. When we ponder why galaxies hold together or what dark energy could be, we are not just solving equations, we are engaging in a story as old as humanity itself, the story of our quest to find our place in the universe. This shared journey matters because it cultivates a scientific mindset in our culture, encouraging critical thinking and a sense of wonder in people of all ages and backgrounds. As astrophysicist Neil deGrasse Tyson often highlights, cosmic mysteries are a gateway drug to a lifelong passion for science. They remind us that the universe is a place of endless discovery and that we are all invited to participate. This is not merely an abstract idea. Today, thousands of people are directly contributing to this grand investigation through citizen science projects. Online platforms allow anyone with an internet connection to help astronomers analyze vast datasets. searching for the subtle arcs of gravitationally lensed galaxies or classifying strange celestial objects that computers might miss. Every pair of eyes scanning these digital skies adds to the effort, turning the public from passive observers into active collaborators in the greatest detective story ever told. This communal engagement is vital. It builds broad, foundational support for the basic research that drives our understanding forward, ensuring that society values the long, often difficult pursuit of knowledge for its own sake. Furthermore, it invites diverse perspectives because the most profound puzzles often require us to think in ways we have not yet imagined, drawing from philosophy, art, and technology. The gravity illusion is more than a technical problem for physicists. It is a human story that challenges us to think bigger, to look deeper, and to remember that we are all part of a species capable of questioning the very fabric of reality. This collective endeavor, fueled by public wonder and expert insight, is how we will ultimately piece together the true nature of the force that binds the cosmos. The most stubborn problems in physics rarely yield to a single field of expertise. A new kind of science is emerging, one that deliberately smashes the walls between disciplines to confront the mystery of gravity. This is not just physicists talking to each other, but a vibrant collaboration with mathematicians, computer scientists, and even biologists. Their unique perspectives are injecting fresh life into a century-old puzzle. Consider the theory of emergent gravity, which views gravity as a consequence of entropy and information. This idea leans heavily on concepts from information theory, a field originally developed for communication and computing. It treats the fabric of space as a complex data structure, and the force we call gravity as a statistical trend toward disorder. Here, a physicist must think like a computer scientist, analyzing the cosmic code that underlies reality. Meanwhile, the deluge of data from telescopes and gravitational wave observatories is so vast that no human can sift through it all. Machine learning algorithms designed by computer scientists are now essential partners. They scan the heavens for subtle patterns, searching for anomalous lensing events or strange echoes in gravitational waves that might betray a crack in Einstein's framework. These algorithms can see correlations and connections that would be invisible to the human eye, acting as digital oracles guiding theorists toward new questions. This interdisciplinary push mirrors the greatest breakthroughs in history. The birth of calculus, essential for Newton's laws, came from the cross-pollination of mathematics and physics. Einstein's own work was deeply informed by philosophy and geometry. The message is clear: the gravity illusion is so profound that it demands an arsenal of intellectual tools. A biologist's understanding of complex, self-organizing systems might inspire a new model of spacetime. A mathematician's work on knot theory could provide the language for the loops in loop quantum gravity. By embracing this diversity of thought, we are not diluting physics, we are strengthening it. We are building a collective intelligence capable of seeing the whole board, not just one corner. This collaborative spirit naturally extends into the most powerful tool of theoretical physics, the thought experiment, where the mind itself becomes the laboratory for the universe. Einstein once pictured himself chasing a beam of light, a simple daydream that unraveled the absolute nature of space and time. This is the power of the thought experiment, a laboratory of the mind where physicists test the limits of reality without a single piece of equipment. Today, this tradition is more vital than ever, as modern theorists confront the gravity illusion with scenarios that stretch our intuition to the breaking point. Imagine, for instance, throwing a single encyclopedia into a black hole. According to Einstein, it is gone forever, lost behind the event horizon. but quantum mechanics insists the information within that book can never be truly destroyed. So where did it go? This is the black hole information paradox, a thought experiment that forces a direct conflict between our two best theories of reality. To resolve it, physicists like Leonard Susskind were driven to the holographic principle, the mind-bending idea that all the information describing a three-dimensional volume of space can be perfectly encoded on its two-dimensional boundary. The book is not lost inside. Its information is smeared like a complex tattoo across the black hole's surface, slowly leaking back out as Hawking radiation. This conceptual leap did not come from a new calculation, but from following a thought experiment to its logical, if unbelievable, conclusion. Philosophers of science like David Albert emphasize that these tools are not mere games. They strip away complex mathematics to expose the core conceptual problems, the places where our language and our logic fail. They help us visualize what it means for space-time to be emergent, or for time to be an illusion. What happens if you try to measure the position of an electron with a scale so sensitive it uses gravity itself? Thought experiments reveal that at a certain point, the very act of measurement would create a tiny black hole, blurring the result into nonsense. This shows that gravity must have a quantum nature, that the smooth stage must be built from discrete, jittering pieces. These imaginative scenarios act as a crucial bridge. They translate the abstract symbols of mathematics into physical situations we can almost feel, making the profound strangeness of quantum gravity tangible. They are the playgrounds where new physics is born, guiding theorists toward equations that might one day describe a universe far stranger than Einstein ever dreamed. This willingness to question the most basic assumptions, to follow a wild idea with rigorous logic, is what prepares us for the final frontier of experimental tests, where the mind's predictions meet the cold, hard data of reality. A new generation of quantum sensors can now measure gravity's pull with such sensitivity they feel the weight of a single virus. This is the vanguard of a technological revolution, one poised to turn the philosophical problem of quantum gravity into an experimental science. Instead of needing a particle accelerator the size of a solar system, physicists are building tabletop experiments that use supercooled atoms and quantum entanglement to probe the fabric of spacetime itself. By watching how these delicate quantum systems behave in a gravitational field, researchers hope to spot the minuscule jitter of spacetime foam or find evidence that gravity does, in fact, have a quantum nature. These are not thought experiments anymore. They are blueprints for machines that will listen for the universe's quietest whispers. Above us, a new eye on the cosmos is opening. The James Webb Space Telescope peers back to the dawn of the first galaxies, studying their rotation and formation with unprecedented clarity. Its data will deliver a decisive verdict on the dark matter debate, revealing whether the invisible scaffolding aligns perfectly with predictions or if the anomalies point toward a modification of gravity. Further ahead, the Einstein telescope, a future underground gravitational wave observatory, will detect thousands of black hole mergers each year. Its exquisite sensitivity will map the ripples in spacetime with such precision that any tiny deviation from Einstein's predictions, any faint echo from a quantum-structured event horizon, will stand out like a single wrong note in a symphony. We are on the cusp of reading the fine print of general relativity, searching for the clauses we never knew were there. The ultimate prize would be to capture the faint echo of the Big Bang itself. Cosmologists are hunting for a specific type of gravitational wave, one generated during the violent inflation of the universe's first instant. These primordial waves, if detected, would carry a direct, unaltered message from the era when gravity and quantum forces were unified. They would tell us what powered inflation and reveal the true nature of the energy that birthed the cosmos. Finding them would be like discovering the cosmic equivalent of the Rosetta Stone. Experts across the globe suggest that within this century, the cumulative weight of data from these diverse missions could force a paradigm shift. The persistent illusion of gravity as a fundamental force may finally dissolve, revealing it as an emergent phenomenon, a statistical trend born from the entanglement of quantum information. The pace of this discovery is accelerating, driven by unprecedented global collaboration where data from a space telescope informs the design of a tabletop experiment, and a gravitational wave detection sparks a new line of mathematical inquiry. Our journey through the gravity illusion reveals a universe far more strange and wonderful than we ever supposed. From Einstein's brilliant geometric insight to the confounding mysteries of dark energy and singularities, we have seen how each answer births deeper questions. We have learned that the force that grounds us is also the force that most confounds us, a reminder that reality's deepest truths are often hidden in plain sight. The greatest discovery may not be a single equation, but a new way of seeing, a recognition that we are part of a cosmic story still being written, one whose next chapter is waiting to be read. The equations of general relativity are written in the language of differential geometry, a form of mathematics that describes curved surfaces and spaces. When Einstein needed a framework for his idea that gravity is the curvature of spacetime, he found that mathematicians had already built the perfect vocabulary. This is a recurring miracle in physics, that pure mathematical exploration, often conducted with no thought for practical application, later provides the precise grammar to describe the cosmos. The tensor calculus that forms the backbone of relativity is not just a set of symbols, it is a profound statement about how quantities transform across a warped landscape, giving us the tools to calculate the bending of starlight or the slow precession of Mercury's orbit. This mathematical beauty is not merely aesthetic, it is functional. As mathematician Roger Penrose has often noted, the world seems to be written in mathematics of a very particular kind, one that is both powerful and strangely accessible to the human mind. The same pattern holds for the challengers to Einstein's throne. The modified gravity theory known as MUND relies on a specific mathematical tweak to Newton's law. The ambitious architecture of string theory is built upon the intricate shapes of Calabi-Yau manifolds, complex geometries that determine the properties of particles in our universe. Each proposed solution to the gravity illusion is, at its heart, a new mathematical structure vying to describe reality. But what happens when our current mathematical languages fail? The quest for quantum gravity is pushing us toward even more abstract territories. Topology, the study of properties that remain unchanged even when an object is stretched or twisted, becomes crucial for understanding the possible shapes of hidden dimensions. Category theory, which focuses on the relationships between mathematical objects rather than the objects themselves, offers a bird's-eye view that could unify disparate physical concepts. Some researchers are exploring non-commutative geometry, where the very concept of a point in space becomes fuzzy, and the order in which you perform measurements matters profoundly. This is not mathematics for its own sake, it is a necessary expedition into uncharted conceptual lands. Our human intuition, forged in a world of medium-sized objects moving at slow speeds, is a hopeless guide in the realms of the ultra-large and the ultra-small. We must rely on the compass of mathematics to lead us. It allows us to reason reliably about realities we cannot visualize, from the frothing chaos of space-time foam to the holographic encoding of information on a black hole's surface. The mathematical frameworks we develop do not just model the universe, they often predict new phenomena that were previously unimaginable. The abstract language of mathematics is our only hope for transcending the gravity illusion, for peering behind the cosmic curtain to see the machinery that actually powers the show. This deep interplay between mathematical invention and physical discovery will undoubtedly shape the next great leap in our understanding, proving that the pen in the hands of a theorist can indeed rewrite the cosmos. Every fundamental shift in our understanding of the universe carries a profound responsibility. The quest to solve the gravity illusion is far more than an abstract puzzle. It is a search for a key that could unlock technologies we can barely conceive. Imagine controlling gravity as effortlessly as we manipulate electromagnetism, the force behind our phones and power grids. The ability to manipulate gravitational fields could revolutionize everything. Spacecraft might no longer require massive rockets, instead riding manipulated spacetime like a surfer on a wave, making the solar system our backyard. Energy production could be transformed, tapping into the cosmic background of spacetime itself. Communication might occur through gravitational waves, bypassing conventional signals to send messages through the fabric of the cosmos, unaffected by any obstacle. Yet with such power comes a deep ethical imperative. Who controls this knowledge and for what purpose? The same principles that could enable clean, limitless energy and open the stars might also be weaponized, creating fields of immense pressure or crafting new forms of propulsion for devastating conflict. Experts in science ethics consistently warn that the pursuit of pure knowledge must be accompanied by a parallel development of ethical frameworks. We must ask not only if we can understand gravity, but how we should apply that understanding. The goal is to ensure these discoveries uplift all of humanity, rather than creating new divides or tools of control. This stewardship extends beyond immediate applications to our very philosophy. Grasping that gravity is an emergent illusion, not a fundamental force, would complete a Copernican-level revolution in our self-perception. It would tell us that the stage upon which we live is not a fixed background, but a dynamic, collective construct. This realization could reshape our relationship with the cosmos, fostering a new humility and a deeper sense of connection to the underlying quantum reality from which we arise. Our journey through the gravity illusion has taken us from Einstein's curved spacetime to the edge of black holes, through the mysteries of dark matter and dark energy, and into the speculative realms of strings and loops. We have seen how our most trusted equations break down at the extremes, pointing toward a deeper, more unified truth. The force that seems so concrete and familiar is the very thing that reveals the universe's greatest secrets are still hidden, waiting for the next curious mind to uncover them. The story of gravity is ultimately the story of our endless, wondrous quest to understand our place in the cosmos. Our journey through the gravity illusion reveals a cosmos far stranger than Einstein's elegant stage. We have seen how his beautiful theory of curved spacetime stumbles when it meets the quantum world, leaving us with profound mysteries like dark matter's invisible grip and dark energy's cosmic push. These are not minor puzzles, they are fundamental cracks in our understanding of reality. They remind us that science is not a destination, but an endless expedition. Every answer we uncover simply peels back a layer, revealing deeper, more fascinating questions beneath. The force that grounds us to this planet, that guides the planets in their dance, remains the most profound enigma in all of physics. Let this exploration be an invitation to perpetual curiosity. The next time you look up at the night sky, remember that you are not just looking at points of light, you are witnessing an ongoing cosmic drama, a story whose deepest truths are still being written. The greatest discoveries often begin not with an answer, but with a question. What part of this cosmic mystery captivates you the most? Share your thoughts and join the conversation below. And if you are ready to continue exploring the universe's deepest secrets, subscribe for more journeys to the edge of understanding. Our shared adventure into the unknown has